Welcome everyone to Birmingham. Now, there are a number of innovations that are now mainstream that come from nature. The Pacific yew tree has given us from the bark a Taxol, which is a very potent anti-cancer agent. In the 18th century, a physician called William Withering cured someone with dropsy, a lady with dropsy, using the leaves of Digitalis purpura, or the common foxglove, and that is cardiac glycoside from that plant. The fungus that grows on Claviceps purpura, the rye plant, called ergot, produces ergometrine, which is used widely in obstetrics to deliver healthy children. Alexander Fleming, of course, from less good laboratory techniques, had a contaminant of fungus onto his petri dish and discovered penicillin's activity. Banting and Best made the link between pancreatic extract and diabetes. And finally, we have honey, which has been around much longer than any of these, about 5 million years, to produce reactive oxygen. And it's the smart technology that evolves the effectiveness and puts it into practice. My interest in all of this is antibiotic resistance. And we've heard a lot about antibiotic resistance in the press over the last few years. And this is a report from Lord O'Neill, and he's identified that now that there's at least 50,000 deaths a year in the EU, probably 700,000 worldwide, at a cost of 1.5 billion in the EU. But if you think it's bad now, the prediction is that it's going to be seriously bad in 2050, with 10 million deaths a year. So it's going to eclipse deaths from cancer, and 100 trillion effects on the world GDP, which is probably a bit more than it's in the Panama bank accounts at the moment. So it is really projected to be a serious problem. And hopefully by smart use of antiseptic, antimicrobial technologies, we can evolve solutions for that. I'm pleased to say that there are around about 12 collaborators presenting work today here. So this is the defined research program for Sergi Honey reactive oxygen, sort of colleagues from Manchester, Southampton, Birmingham, Sligo, Imperial, as well as a number of NHS institutions are all here today and presenting. When I was Director of Research and Development, we were keen to look at, and certainly the government research program, the NIHR, is very keen to look at translational research. And translational research is about taking an idea and proving its use in particular parts of the research cycle. So we've got a number of translational pathways going from the individual molecules into parts of cells, cells into organisms, organisms into humans, and humans into society. And each of those pathways are the translational gap that hopefully we will describe to you today. So we'll be seeing a lot of microbiology going from antibacterial, antiviral, antifungal, looking at the various potencies of this compound, and some of the clinical experience, putting it into chronic wounds, acute wounds, and a number of specialist areas that there is a lot of interest and a lot of research being developed. So, I thought I'd open this session with a brief outline of reactive oxygen and where it sort of fits into normal and abnormal cell and human usage. So we're going to have, and I do apologize for this, we're going to have some chemistry lessons. We're going to have some physiology lessons. So those of you who aren't chemists and physiologists or pharmacologists, I apologize, but hopefully you'll get a little bit more of an understanding of what we're talking about today. Okay, so this is the chemistry bit. Okay, so oxygen is a symbol O or O2. It's got an atomic mass of 16, atomic number of 8. It's got a few electrons floating around the nucleus. Obviously, it's a gas with a melting point of minus 218 degrees Celsius, which is pretty cold. And there's some, they now believe they're co-discoverers of Carl Wilhelm Scheele and Joseph Priestley discovered oxygen. And we know that it's an essential substrate for mitochondrial adenosine triphosphate. Basically, that's the energy driver for the whole of organisms. But it has another role in wound healing, supplying increased amounts of energy requiring for tissue recovery and renewal. So it is ubiquitous, we're breathing it in all the time, but all it's at a micromolecular level, at a cellular level, it's processing all the time. Reactive oxygen is oxygen which is slightly altered. And reactive oxygen is used physiologically as a signaling messenger to get things going within cells. And reactive oxygen applies to molecules containing oxygen, but as I say, which have been reduced with added electrons. So it's made it very reactive to have a free radical format. So there are a number of reactive oxygen species. So we have peroxide, superoxide anion, hydrogen peroxide, which most of you will be familiar with, and actually is the basis of the reactive oxygen method of action of Sergio Honey. Hydroxyl radicals, hydroxyl ions, and all have different actions and reactions within the cell processes, both endogenously, i.e. sort of as a part of the normal physiological processes, but also increasingly is being used exogenously, added as an additional external stimulus to produce benefits. So if you want to read about reactive oxygen and wounds, this was a review that we wrote last year. We got published last year in the International Wound Journal. And it talks about the actual physiological processes that are going on in the wound cycle, the wound healing cycle, but also points some way to new and innovative compounds that are coming through, which might be of value in our society. So, we're getting on to the physiology lessons now. So we know that reactive oxygen is secondary messengers to immunocytes and lymphoid cells, which are normal processes involved in wound healing. and coordinating the recruitment of lymphoid cells. There's some evidence that reactive oxygen stimulates the generation of new blood vessels, which is a term called angiogenesis. And certainly it has a role in signaling phagocytes and antiseptic and antimicrobial activity when there are infections present. So let's look at what happens with a wound. So if you look here, imagine you have a cut. What happens? It bleeds. The red blood cells, the erythrocytes, pour out. But interestingly, the reason why bleeding stops initially is because the blood vessels contract, and they contract due to a signaling of reactive oxygen. The contact of the platelets with the external collagen and ECM stimulates them to form an adhesive mass, and then the red blood cells coagulate and you get the thrombin formation, the thrombus formation. So that's all stimulated and enhanced by hydrogen peroxide reactive oxygen. Then if you look at what happens next, lymphocytes are stimulated again by reactive oxygen to migrate to the sites, to turn into neutrophils, where they can act as anti-inflammatory mediators and generate part of the tissue repair process. We then have the activity of these neutrophils. They eat up the bacteria and fungi that might be present, and again that is generated from reactive oxygen signaling, and also excrete hydrogen peroxide, which is an antiseptic, an antimicrobial agent locally. We then have lymphocytes recruited, which come in, and monocytes, which come into the area. And then finally, tissue repair stimulates keratinocytes, endothelial cells to form angiogenesis and fibroblasts and collagen formation. Basically, this is new blood vessels, basic scar tissue, and involve in healing repair. And very simply, that's what happens in the surgical process and the role of reactive oxygen in facilitating that. So the key messages that we have here are pivotal in the normal wound healing process. It acts as secondary messages to many immunocytes and lymphoid cells. It acts in the early host defense against infection. We can exploit these roles in clinical practice, in therapeutic strategies, and we'll be talking about these later today. And particularly in chronic leg ulcers, pressure injury, and surgical wounds and burns. And there are a lot of things which potentially can be used for generating wound healing and antiseptic activity. And if you look at the concentration effects of reactive oxygen physiologically, then if you've got very low levels, then you can get cell cycle arrest. And that's what happens in chronic venous ulcers, diabetic leg ulcers. They don't have any blood supply, and they don't have reactive oxygen in order to generate this tissue repair. Basal levels are essential for normal cell functioning. Increased levels can produce cell-mediated defenses, but when we're in excess production, can cause problems and cellular toxicity. So in terms of wound infections and wound healings, we know that we have problems associated with colonization with microorganisms and biofilms. We know we use too many unnecessary antibiotics. There are toxic or ineffectual topical antimicrobial agents that are used currently. And as I say, we've got the real problem of antimicrobial resistance. So if we just concentrate on this little bit here, which is the antimicrobial activity, we know that if we administer hydrogen peroxide as an example of a reactive oxygen donor, exogenously, i.e. externally, then we know it reacts with certain chemicals within enzymes and proteins and DNA in the bacterial cell membrane, causing death. It has a topical activity, so it's a local effect. It's certainly concentration dependent, so the more there is there, then the more effective as an antimicrobial it'll be. But conversely, the more that's there, potentially the more toxic it can be to host cells. And interestingly, there's been no cases of antimicrobial resistance identified to this molecule at all whatsoever. So it is persistently lethal to certainly bacterial organisms. We did some work with the Institute of Science in Sligo in the Irish Republic, looking at seeing if there was a relation between the generation of hydrogen peroxide and the antimicrobial activity, the antibacterial activity. And basically, they looked at the existing Surgery Honey ROS and looked at the hydrogen peroxide generation over a 24-hour period. And then because it's a smart bioengineered product, they were able to manufacture 2 prototypes which were even more potent. And this is an example of sort of science developing from, again, natural substances. And you can see there's quite a high hydrogen peroxide generation. And then if you compare that, and this is the hydrogen peroxide activity with the percent phenol activity, which is against Staphylococcus, which is a normal skin organism. So the higher the concentration of phenolic activity, the more antibacterial, antimicrobial it is. There is a linear relationship between the amount of peroxide generated and the antimicrobial activity. And this is something which you would expect, but this is something which was demonstrated in this particular paper. When we develop agents for therapeutic use, there are a number of steps that we've got to go through. And bear with me on these pharmacological terms. You won't be tested at the end of this, by the way. So we've got pharmacodynamics, PD, and this is, does something work at the site that it's supposed to work at? Does it work? And we have pharmacokinetics, which is, does it get to the site that it's supposed to work? So the kinetics bit is can you transmit it to the site? Well, clearly with a wound, if you've got a plaster and you put it onto the wound, you're actually doing that. But you'll be hearing today some more sophisticated ways of delivering reactive oxygen to areas which are not generally easily accessible. So that's pharmacokinetics, and the PK/PD values are very useful in the initial identification of value of new entities. And of course, we've got safety and tolerance. It's no good producing something which works very well in the lab, but it's very toxic when you put it into humans. So we have to do safety and tolerance studies. And then, does it work in the clinical environment, in the sorts of clinical conditions that we face on a day-to-day basis? Chronic wounds, acute wounds, and you will see some evidence of that. And finally, is it worth it? It's no good sort of paying a king's ransom for something if we can't afford it as a society. So, does it work? Is it safe? And is it worth it? Are all parts of the program to develop a new therapeutic entity. It does work, and I'm stealing a couple of Matthew's slides here. I'm sorry about that, Matthew, but these are published slides saying that it works to prevent infections in cesarean wound infections, and it works in eradicating and preventing infections in along lines that are used for treating cancer patients. But for those of you who have had your teeth whitened, it's also used. Not hydrogen peroxide as such, but there's a warning that too much can cause toxicity, and this was in the BBC News last week, to say that some unlicensed dentists or unlicensed beauticians are using inappropriate peroxide gels to whiten teeth. So again, it's about dose, and it's about safety, and it's about effectiveness. Okay, so thank you very much.